Okay, for example 3, one graph isn't always enough. We want to graph the function f of x, which is equal to x squared times x plus 1 cubed over x minus 2 squared times x minus 4 to the 4th power. So let's first graph this function similarly to how we did it in a previous example by using the viewing rectangle to be negative 10 to 10. So let's go ahead and do that here. Okay, x minus 2 squared times x minus 4 to the 4th power. Okay, so let's put in the viewing rectangle of negative 10 to 10, and also for the y-axis from negative 10 to 10 as well. Okay, so what we can see here is that we have a graph that shows here the function f of x. Okay, and from this figure, we have the feeling that we're probably going to have to zoom in a little further to see some more finer detail. But as a guide for zooming, let's first take a look at the function. Okay, so let me go ahead and copy this graph here. Okay, so let's take a look at the function. So what does the function actually look like from what we put in? Well, look at the denominator. Okay, if we look at the denominator, okay, and this being the first graph here, if we look at the denominator, we have x minus 2 squared and x minus 4 to the 4th. So when we look at that, okay, from this graph, again, we see that we're going to have to zoom in a little further. But because of the factors x minus 2 squared and x minus 4 to the 4th power in the denominator, we would expect that x equals 2 and x equals 4 to be the vertical asymptotes. Okay, so let's check. So if we check, we want to take the limit as x is approaching 2 of the function x squared times x plus 1 cubed over x minus 2 squared times x minus 4 to the 4th. Okay, well that is equal to infinity. Okay, and then if we want to find the limit as x is approaching 4 of the function x squared times x plus 1 cubed over x minus 2 squared times x minus 4 to the 4th, that is also equal to infinity. Okay, so now what we want to do is we want to find the horizontal asymptotes. So in order for us to find the horizontal asymptotes, we need to divide the numerator and denominator by x to the 6th. So let's go ahead and do that. So we have the function, which is x squared times x plus 1 cubed over x minus 2 squared times x minus 4 to the 4th, right? And we're dividing this by x to the 6th, and we're dividing this by x to the 6th, and we're dividing this by x to the 6th as well. Okay, so we can rewrite x to the 6th to be the following. So we know that in the numerator it's going to be x squared over x cubed times x plus 1 cubed divided by x cubed, because x cubed times x cubed is going to give us x to the 6th. And the same thing here, we have x minus 2 squared over x to the 2nd times x minus 4 to the 4th power times x to the 4th, because again, x squared times x to the 4th gives us x to the 6th. Okay, So now what we can do is we can simplify this a little further. So simplifying this further, x squared divided by x cubed is 1 over x. And then here we're going to have x plus 1 over x now, and that's cubed. And then in the denominator, we're going to have x minus 2 over x squared. And then that's x minus 4 over x to the 4th. So now we can simplify what we have in the parentheses. So that x over x becomes 1, and then it's plus 1 over x by separating those. And that's cubed. And then over here, we're going to have 1 minus 2 over x, and that's squared, times 1 minus 4 over x to the 4th power. So what does this show? Well, this shows the fact that as f of x approaches 0, so as the function approaches 0, as x is approaching plus or minus infinity. So now let's graph this with the vertical asymptotes. So we know that one of our asymptotes is x is equal to 2. Okay, so we're going to make that, there's one of our vertical asymptotes. Okay, and then we have another one at x is equal to 4. Okay, and so let's just kind of zoom in a little bit on this. So we're going to go from, let's say, -2 to 4 of our graph. Maybe let's go to 5. And then here we'll just go from -1 to, let's say, 4. Okay. So maybe expand it a little bit more so we can see what's happening here. So here we have our graph where we can see the vertical asymptotes. So let's go ahead and take a look at that here. So we're going to call this graph number 2. Okay, we can see that we have a vertical asymptote at x is equal to 2. And also a vertical asymptote at x is equal to 4. Okay. Okay, now let's take a look at this graph here. So when we look at this graph, it is also very useful to consider the behavior of the graph near the x-intercepts. Now, since x squared is positive, the function does not change sign at 0. And so its graph doesn't cross the x-axis at 0. But because of the factor in the numerator, x plus 1 cubed, the graph does cross the x-axis at -1 and has a horizontal tangent there. Putting all this information together, but without using derivatives, we see that the curve has to look something like the one in graph number 2. Okay, now what we can do is, now we want to know what to look for, so we need to zoom in several times to produce the following graphs 3 and 4, and then we're going to zoom out several times to get the graph of 5. Okay, so let's take a look at these graphs. We got graphs 3, 4, and 5. Okay, so the viewing rectangle here was going from -100 to 1, and then -0.05 to +0.05. And then the viewing rectangle in number 4 had gone from -1.5 to 0.5, and then -0.001 here, or in this case we can go to 5, and -0.0007. And then for number 5, the viewing rectangle had gone from -1 to 10, and then from negative 10 to 500. Okay, so I want you to pay attention to the points that were there. So we can read from these graphs, okay, that the absolute minimum is about negative 0.02 and occurs when x is negative 20. So there is the absolute minimum. Okay, there is also a local maximum when it's approximately 0.0002, when x is approximately negative 0.3, which we see there. Okay, and we also have a local minimum at approximately 211 when x is approximately 2.5. So these graphs also show 3 inflection points near negative 35. So we have an inflection point near negative 35. Okay, we also have one at negative 5 and negative 1 here, and also between negative 1 and 0. Okay. So to estimate the inflection points closely, we would need to graph the second derivative, but to compute the second derivative by hand is an unreasonable chore. So if we did have a computer algebra system, then it's easy to do, which is going to be an exercise 13. And so to summarize here, we have seen that for this particular function, 3 graphs, 3, 4, and 5 are necessary to convey all the useful information. The only way to display all these features of the function on a single graph is to draw it by hand. Now, despite the exaggerations and the distortions, graph 2 does manage to summarize the essential nature of the function, which was here. But again, we would need 3, 4, and 5 to get the finer detail.